Hey, it's Mr. Shrum again, and I am back with another mastery test walkthrough for physical science. And we're going to talk about the conservation of momentum. We talked about collisions last time, and we're going to talk about how momentum is conserved in these collisions. So this is the law of the conservation of momentum. And to put that plainly, we say when two objects collide in an isolated system, the net momentum of a system is conserved. All right. So that means the momentum before the collision and the momentum afterwards as a system is the same. And how we get that is we know that momentum, which we put as P, momentum, equals mass times velocity for an object. But when there is more than one object in a situation, like a collision, when two objects collide, you can add up their momentums. So excuse that little mistake. But the momentum of the system equals the mass times velocity of one object plus the mass times velocity of a different object. So that is how we calculate momentum in a collision. And here's another way to put it. P initial, so the initial momentum equals m times the initial velocity plus m2 times the initial velocity for that object. And then afterwards, same thing. So the masses stay the same here, the masses stay the same, but their velocity may change depending on the collision. And we'll use this to solve equations in the mastery test. And we'll set them equal to each other. So if this equals that, then we can put m1 times the initial velocity plus m2 times the initial velocity for that object equals the final version of that. And there are two types of collisions. We talked a bit about that last time, but this will be more in depth. In an inelastic collision, if you remember, last time we talked about elastic collisions. That was when objects with hard surfaces would collide and then bounce off one another without changing their shape. In inelastic collisions, they are able to change shape after they collide. So they have momentum is conserved, right? From the law of the conservation of momentum. Momentum is always conserved, whether it's elastic or inelastic. However, kinetic energy is not conserved in inelastic collisions. And that is because some of that energy is used to deform the shape of these objects. And it could be lost to heat. So Ke is used to deform Ke is lost to heat. So that is where the kinetic energy goes in these situations. And in some of these inelastic collisions, we're going to look at an object will hit another object, but they will collide and then become one unit. And we'll get to talk about that later. But instead of bouncing off one another and then going their separate ways, a lot of the times in inelastic collisions, they hit each other and then they stick together and then have a velocity that is shared. And we'll talk about that in some examples. But in elastic collisions, these guys are easy to deal with. The kinetic energy is conserved, and the momentum for these collisions is conserved as well. So for the steps to solve those problems, it's straightforward. We would use this equation up here, set the initial momentum equal to the final momentum, and you would set the kinetic energy initial equal to the kinetic energy final, because it's all conserved. The difference in inelastic collisions, you would use the momentum equation up here, right? Because that is conserved. So you can set the initial equal to the final and then solve. But the kinetic energy initial is different from the kinetic energy final. So that's a big point to remember. So everything's conserved in elastic collisions. Kinetic energy is not conserved in inelastic collisions. So a way to remember that is the in, not elastic, not conserved for kinetic energy. All right. And with that, we're going to get into some examples from the mastery test. Is that everything? I'll scoot the camera a little bit further. There you go. All right. So in the first situation, we have a ball. We'll call it A. Its mass is 0.2 kilograms and it's traveling with a velocity of 2 meters per second. It collides with a 1 kilogram ball B. And ball B was stationary, which means the velocity was 0 meters per second. So which statements are true? If this is an elastic collision, what statements are true? So you're given multiple choices, but this is the correct response. The balls separate and move in opposite directions. So this is what happens before the collision. Before, after. So before A is moving, B is not moving, they collide, then A and B separate, and now they're going in different directions. All right. Got it? Cool. So for the second question, we're told that a large plastic ball hits a stationary tennis ball. If the plastic ball's mass is 3 times the mass of the tennis ball, then what happens? So I drew it out, give you a better visual. We have this plastic ball. It's going with the velocity. Then it hits the tennis ball, which was stationary. But now after that, they're both moving in this direction. Why is that? Well, if a larger mass hits a stationary smaller mass, the large mass will not change direction. In this instant. So because this is so much larger than this ball and it's traveling at a velocity, this does not have enough momentum to push it back, enough mass and velocity to push this other ball back. So they'll both end up moving this way. So they're both going to move in the same direction. All right, you got that? The next one, oh, let me get some of those out of the way so you can see. So in this third one, elastic collision in one dimension, we have A and B. These balls or objects have equal mass, and B is at rest initially. So at rest, V equals 0. They collide. A will come to a complete stop. B will move with the initial velocity of A. And why is that? Well, we know that the momentums, initial and final, are equal, and we know that the initial kinetic energy is equal to the final kinetic energy. So for P initial, we have MA times VA, and B does not have momentum because there's no velocity right then. So that's what we get. And so plus MB V B F. And if K kinetic energy is conserved, then we have 1/2 M A V A squared. Now it'd have to equal 1/2 M A V A F squared plus 1/2 M B V B F squared. Okay. Well, but if they have the same mass and they collide, A was going to stop and then B will move with the initial velocity of A. So it's like a billiards table or a pool. So you hit the cue ball hits the ball, and then in this situation, the cue ball will completely stop, and then this ball will move. And that happens in elastic situations. But sometimes that's not always the case. In the next problem, we're talking about cars colliding. So we have car 1 with mass 1.5, 1.5 times 10 to the third power kilograms, and it was going at a velocity of 22 meters per second, moving in the west direction. There is a second car with a mass of 9.0 times 10 to the second power kilograms. And it's at rest, so it's stationary. It had no velocity. If the first car hits the second car in an inelastic collision, what is the final direction and velocity of the two cars? So here's before, and here's after. So they've collided. They're both going to move in the westward direction. And since it's inelastic, they're not going to be moving with the same velocity as before. So it's going to be between 0 and 22 because some of that is lost. So the answer is they're going to move west at about 14 meters per second. And that's between 0 and 22. So that checks out. In an elastic one, see, elastic, all of that gets transferred to the next one, and that's why B will move with the initial velocity of A, and then A will stop in that third one. But for the car's mass, in this one, it's inelastic, so they're gonna collide, and then they're gonna move towards this way together. And that's gonna be between 0 and 22 meters per second. Then we have 5. If a truck hits a stationary car, the car will deform and heat will be generated, because this is an example of inelastic. So when you think of cars, car collision, inelastic. So a car collision is inelastic. Inelastic means kinetic energy is not conserved. The car will deform and heat, and the kinetic energy of the system is partially used to deform the car. Okay? Let me know if that isn't clear for you all. And then I can give you some more examples and maybe we can work it out. But for number 6, we have a small ball with a mass of 2 kilograms and a velocity of 1.5. Uglier. 1.5 meters per second. And then a larger ball has more mass of 5 kilograms, but it's stationary at rest. Velocity is 0. And we want to know what is the kinetic energy of the system after the collision. So we have a small ball hitting a larger ball. So, and then what happens? So V 1.5, V equals 0 for this one. Small, large ball. Well, this will be an elastic. because these are hard surfaces, their shape is not going to deform. So that means kinetic energy is conserved. Kinetic energy is conserved. So we plug in the masses and velocities into this equation. And since we know the initial kinetic energy will be the same as the final, we can just find the initial kinetic energy, right? Because that is easier to calculate. Anytime one of your objects has a velocity of 0 at the start and it's an elastic collision, calculate that before, because then you can cancel out a whole term. So here we have the initial kinetic energy equals 1/2 the mass of the small ball times the velocity of the small ball initially squared, plus 1/2 times the mass of the large ball times the velocity of the large ball squared initially. But this is 0, right? Because it was at rest initially. So we can cross that out. So it'll be 1/2 times 2 kilograms times 1.5 meters per second squared plus 0. So just ignore that second large ball term and then just calculate that. And you get 2.25 joules. And since kinetic energy is initial equals kinetic energy final, 2.25 joules. Joules is our SI unit for energy. And we J. All right. Just get a good look at all that. But this is the question we were asked. And since these are balls, hard objects that do not change shape, it's an elastic collision, which means kinetic energy before and after is the same. And then we found kinetic energy before because it's easier to calculate. And the kinetic energy before equals kinetic energy after. So we get 2.25. All right. Cool. All right. Just trying to make this as clear as I can. And in 7, we're given another example. I'm talking about bumper cars. So remember when you could ride bumper cars? Yeah, that was a while ago now. But car 1 has a mass of 200 kilograms and a velocity of 3.5 meters per second before the collision. Then there's a second bumper car. It has a mass of 250 kilograms. And we're told, or we're asked, if they collide and stick together, that's a big red flag, and move at a velocity of 2.3 meters per second, what's the kinetic energy of the system after the collision? Well, this is an inelastic collision, meaning that they stick together and they're moving together as a unit at a velocity of 2.3. So to find the final kinetic energy, we just plug in 1/2 m1 times final velocity squared plus 1/2 m2 times final velocity squared. And you can simplify this because these velocities are the same. So you can just add these terms together. So we get 1/2 times m1 plus m2 times final velocity squared. So we have kinetic energy final equals 1/2 times 200 kilograms plus 250 kilograms. That's from stuff we already know up here, m1 and m2. And then we have and then we have the final velocity too. We're told that after the collision, they're moving at 2.3 meters per second. So after that, you get 1/2 times 450 kilograms times 2.3 squared, and you get 1,200 joules. But the answers are given in scientific notation, so you have to put a decimal place there, and then multiply by 10 to the third power. Well, these numbers are the same. And let me know if you need a refresher on scientific notation. 1, 2, 3. That's all it means. 10 to the 3 means you're moving the decimal over 3 times. Okay, good pattern to get into. Then we have 8. Ignore that bottom stuff. But here, that's all you need to see. We have object A with mass 500 kilograms, and it hits a stationary object B, which means VB equals 0 meters per second initially. If collision is elastic, what happens after the collision? So if it's elastic, what happens after the collision? Well, object B will move forward. Object A will push B, and it'll move that way. But the mass of B means that A is going to be directed in the opposite direction. Okay? And I think you just intuitively can get a feel for why that is, because B is so much bigger and A just doesn't have enough power to overpower it completely. It can get it to move, but it will also receive a force strong enough to change direction. And if it's an elastic collision, you know that momentum is conserved and kinetic energy is conserved. So we can look at, yeah, let's go over here and look at the initial momentum. B is not moving, so it doesn't have any momentum to contribute. So it is just MA times VA, which is 500 kilograms times VA. And then we have final momentum equals 500 kg, the final velocity of A plus 920 kilograms times final velocity of B. And in that situation, if the initial velocity equals this, then these velocities have to be they have to change, right? 500 kilograms times the initial velocity of A, 920 kilograms times velocity of B. That means that this velocity has to be negative to make sure that initial momentum equals final momentum. And making a velocity negative changes the direction. So because B's mass is so big, to make sure these calculations are correct, to come out correct, V has to be negative to balance out the big mass of object B, okay? And negative velocity for A means that it changes direction backwards. It's all about the conservation of momentum. And then we'll look at another example that will show you that in another way too. So this one will be inelastic. We have a large mass colliding with a smaller stationary mass. Stationary means velocity is 0 initially. How will the masses behave if the collision is inelastic, meaning that the objects will not separate and they will actually be sticking together. Inelastic means they will stick together and move together, right? So they'll initially start out like this. A large mass will have some velocity, L for large, and then this will be small. And it'll initially be 0, right? So this one hits that, and then they stick together, and then they're moving together with a different velocity. But if it were elastic, so this is just hypothetical now, if it were elastic, they would fly apart and not stick together. So inelastic, stick together, and their kinetic energy would change. If it's elastic, they would fly apart and not stick together. Kinetic energy would be the same before and after the collision. So here's another way to look at that. But anytime one mass is significantly larger than another object, there will be a major stoppage. So V could be 0 or V could be negative. So if something's really massive and something else hits it, the other object would stop, or it could be reversed direction. So it could stop, or it could change direction. But yeah, that's about it for the mastery test about the conservation of momentum in collisions. If you have more questions, be sure to hit me up in Canvas and I will help you as much as possible. So have a great rest of your day and or week, and I will see you guys later. Bye.